Neptune's upper atmosphere has cooled by several hundred degrees in just 3 decades, and nobody expected it. Scientists using the James Webb Space Telescope caught something that Voyager 2 completely missed back in 1989, and it has rewritten what we thought we understood about the outermost planet in our solar system. For over 30 years, one of the most basic features of Neptune stayed hidden from every telescope on Earth and every instrument in orbit. Then, in June 2023, Webb pointed its near-infrared spectrograph at this distant blue world, and the data that came back left researchers stunned. This is the story of how a routine observation turned into one of the most surprising discoveries in modern planetary science, and why astronomers are still trying to explain what is happening 800 million miles away from home. Neptune was discovered in 1846, and for the entire history of human observation, it has remained the most distant and least understood planet in our solar system. It sits roughly 30 times farther from the sun than Earth does, out in a region so cold and so dim that sunlight reaching its clouds is nearly 1,000 times weaker than what reaches us. Along with Uranus, Neptune belongs to a category astronomers call ice giants, a class of planet distinct from the gas giants Jupiter and Saturn. Ice giants are built from a different mix of materials, dominated by water, ammonia, and methane ices surrounding a rocky core wrapped in a hydrogen and helium atmosphere. Because of the sheer distance involved, only one spacecraft in history has ever visited Neptune up close. NASA's Voyager 2 flew past the planet in 1989, capturing images and readings that became the foundation for almost everything textbooks have said about Neptune ever since. Every model of its atmosphere, every assumption about its temperature, every theory about its rings and moons traced back to that single flyby. For over 3 decades, that data was essentially all we had. Ground-based telescopes could track some changes over time, but they lacked the resolution and sensitivity to answer many of the deeper questions scientists had about Neptune's atmosphere, its magnetic field, and one particular phenomenon that had stubbornly refused to reveal itself: an aurora. Auroras are not unique to Earth. Jupiter, Saturn, and Uranus all display them, glowing displays caused by charged particles slamming into a planet's atmosphere near its magnetic poles, exciting gases and making them glow. Astronomers had long assumed Neptune should have similar activity, since its formation and composition suggested a magnetic field strong enough to produce one. Yet every attempt to detect it failed. Telescope after telescope came up empty. It became one of the quiet, nagging mysteries of planetary science, a phenomenon predicted by every reasonable model and yet completely invisible. That changed with the James Webb Space Telescope. Webb was never designed with Neptune as its primary target. Its main mission involves peering into deep space, studying the earliest galaxies and distant exoplanets, but its instruments are so precise, so sensitive to faint signals, that scientists realized they could also turn it toward objects much closer to home. In 2022, Webb captured its first image of Neptune, and even that initial picture caused a stir among planetary scientists. The image revealed the clearest view of Neptune's rings in more than 30 years, since Voyager 2 first spotted them. Some of those rings had not been detected at all since that 1989 flyby. Alongside the bright, narrow rings, Webb's cameras picked up fainter dust bands circling the planet, bands so faint they had essentially disappeared from view since Voyager's brief past. Heidi Hamel, an interdisciplinary scientist working with the Webb mission and a longtime expert on the Neptune system, described the moment as remarkable. It had been 3 decades since anyone had glimpsed those delicate, dusty rings, and this was the very first time they had ever been observed in infrared light. The precision and stability of Webb's imaging allowed it to detect features so faint and so close to an extremely bright planet that earlier telescopes simply could not resolve them. Along with the rings, that same image revealed 7 of Neptune's 14 known moons. One moon in particular stood out immediately: Triton. Neptune's largest satellite appeared as an almost blinding point of light in the image, complete with the signature diffraction spikes that appear around bright objects in many of Webb's pictures. Triton is unusual among large moons in our solar system because of its orbit. It moves around Neptune backward in what astronomers call a retrograde orbit, opposite to the direction Neptune itself spins. That strange motion has led scientists to a compelling theory. Triton was likely not born alongside Neptune at all. It may have originated far out in the Kuiper Belt, the icy region beyond Neptune filled with small frozen bodies, and was later captured by Neptune's gravity, pulled into an orbit that betrays its foreign origins to this day. That first Webb image alone reshaped how scientists talked about Neptune's rings and moons. But it turned out to be only the opening chapter. The real surprise was still to come, and it arrived almost by accident. Around the same period, another quiet correction was being made to how the public pictures Neptune altogether. Most people know Neptune as a strikingly deep, vivid blue world, an image burned into public memory by decades of Voyager 2 photographs. Those photos, however, were processed in a way that exaggerated the planet's color to bring out contrast and detail, making Neptune appear far bluer than it truly is. A newer analysis using more accurate imaging and processing techniques revealed that Neptune's actual color is closer to a pale, muted blue-green, much more similar in tone to Uranus than previously assumed. That same study also explained why Uranus itself sometimes appears to take on a slightly greener hue in certain images, tracing the effect back to seasonal changes and atmospheric haze rather than any fundamental difference in composition. It was a small but telling reminder that even the most basic facts about these distant worlds, facts most people never think to question, had been shaped as much by imaging techniques as by the planets themselves. But the color correction was nothing compared to what came next. In June 2023, a team of researchers led by Henrik Mellon used Webb's near-infrared spectrograph to study Neptune's middle atmosphere. Their original goal was fairly narrow. They wanted to examine circulation patterns, the way gases move and mix at different altitudes. Or nobody on the team expected to stumble onto the very mystery that had eluded astronomers for over 30 years. As they analyzed the incoming data, they noticed something unexpected embedded in the spectrum. There, unmistakably, was an infrared auroral glow, along with an extraordinarily clear signal from a molecule called H3+, a form of ionized hydrogen that forms in a planet's upper atmosphere when it is bombarded by charged particles. This molecule is one of the clearest fingerprints of auroral activity, and Webb had captured it with a level of clarity nobody had managed before. After decades of failed attempts using ground-based telescopes and other spacecraft, astronomers finally had definitive proof. Neptune does have an aurora. The signal was real, sharp, and undeniable. It was a genuine breakthrough, closing the book on one of the long-standing question marks of our solar system's outer planets. Except the discovery immediately opened up a much bigger and stranger question. Because embedded in that same spectrum was something the researchers had not been searching for at all, a way to directly measure the temperature at the top of Neptune's atmosphere for the first time since Voyager 2's flyby in 1989. And the number that came back did not match anything scientists expected. The intensity of the H3+ emission is directly tied to temperature. The brighter and sharper the signal, the more precisely researchers can calculate how hot or cold that layer of atmosphere actually is. When Mellon and his colleagues ran the numbers, the result was almost unbelievable. Voyager 2 had measured the temperature at the top of Neptune's atmosphere at about 750 Kelvin, roughly 477 degrees Celsius, back in 1989. Webb's new measurement in 2023 put that same layer at just 358 Kelvin, around 85 degrees Celsius. That is not a minor shift. It represents a cool down of several hundred degrees, meaning the temperature Webb measured was just over half of what Voyager 2 had recorded more than 3 decades earlier. Henrik Mellon later admitted just how shocked the team was by that number. He described being astonished that Neptune's upper atmosphere had cooled by hundreds of degrees over that stretch of time, a change far larger than anyone modeling the planet's climate had anticipated. And this is where the real mystery begins, because that cool down does not just answer old questions, it raises entirely new ones. For one thing, the timing does not add up neatly. Neptune's seasons are nothing like Earth's. Because the planet takes about 165 Earth years to complete a single orbit around the Sun, each of its seasons lasts roughly 41 years. A change of this magnitude, if driven purely by Neptune's slow seasonal cycle, should unfold gradually over that kind of multi-decade timescale, evenly and predictably. Instead, this cooling appears to have happened faster than the seasonal clock would suggest, catching researchers off guard. Whatever is driving this change, it does not seem to be simply the planet's long, slow march through its seasons. What makes this even more compelling is that this discovery did not appear out of nowhere. It actually confirmed and extended an earlier finding. Back in 2022, a study led by Michael Roman at the University of Leicester had already flagged something strange happening in Neptune's stratosphere. Using around 2 decades of ground-based observational data, Roman's team identified a dramatic, long-term cooling trend in Neptune's atmospheric temperatures, a trend that did not fit the expected seasonal pattern either. When Webb's 2023 measurements came in, they lined up with and reinforced what Roman's team had already suspected. 2 completely different data sets gathered years apart using different methods were now telling the same unsettling story. Something is cooling Neptune's atmosphere in ways nobody fully understands. And then there is a second, separate strand to this mystery. Around the same period, other observations noted an unseasonably cool summer occurring elsewhere in Neptune's atmosphere, a shift that researchers have specifically said does not appear to be connected to the dramatic upper atmosphere cooling detected through the aurora measurements. In other words, Neptune appears to be a running cold in more than one place, through more than one mechanism, and scientists are not yet able to tie these threads together into a single explanation. It is entirely possible that Neptune's atmosphere is being shaped by several independent processes at once, each poorly understood on its own, now overlapping, to create a planet that behaves in ways nobody predicted even a few years ago. There's also a very practical piece of this puzzle that explains an old scientific dead end. For years, astronomers based their expectations of Neptune's auroral brightness on the temperature Voyager 2 recorded back in 1989. Using that older, much higher temperature, models predicted an aurora that should have been detectable, at least in theory, using existing telescopes. But those predictions never matched reality. Every search came back empty. Now scientists understand why. With the atmosphere running so much colder than assumed, the resulting aurora would be far fainter than anyone had modeled. It was not that Neptune lacked an aurora. It was that the temperature everyone had been using to predict its brightness was wildly out of date, dramatically overestimating how visible that aurora should be. This single discovery didn't just find something new. It resolved 30 years of failed searches by revealing that the target itself had quietly changed while nobody was watching. Beyond the technical detail, that resolution matters because of how it reframes the way we think about a planet like Neptune. For most of the modern space age, distant planets like Neptune have been treated almost like fixed points, worlds captured in a single dramatic snapshot from a single flyby, then left largely unchanged in our collective imagination. Voyager 2's 1989 images became the reference point for everything, repeated in textbooks and documentaries for generations, but Neptune is not frozen in time. Its atmosphere is dynamic, actively shifting over the decades in ways scientists are only now beginning to detect, because we finally have an instrument sensitive enough to catch it. That alone is one of the most important lessons buried inside this story. Many of what we treat as settled facts about the outer solar system were captured during a brief, single moment decades ago, and only now, with tools like Webb, are we discovering how much has changed since then. Researchers are not stopping at a single measurement either. With this cooling trend now confirmed through 2 independent lines of evidence, the priority has shifted toward long-term monitoring. Scientists want to track Neptune with Webb across a full solar cycle, an 11-year stretch tied to the sun's own magnetic activity. The reasoning is straightforward. If the sun's activity is somehow connected to what is happening in Neptune's distant atmosphere, tracking a complete cycle should reveal whether the cooling ebbs and flows in tandem with solar behavior, or whether it continues regardless, pointing to a cause entirely internal to Neptune itself. There's another layer to this that makes the mystery even more tantalizing. Neptune's magnetic field is notoriously strange. Unlike Earth's magnetic field, which is reasonably well aligned with the planet's rotational axis, Neptune's magnetic field is dramatically tilted and offset from its center, producing a magnetosphere that behaves unpredictably compared to what we see closer to home. Scientists studying the aurora and the temperature shift hope that continued observation might eventually shed light on why Neptune's magnetic field is shaped the way it is, a question that has puzzled researchers since Voyager 2 first mapped it in 1989. If the same forces driving the atmospheric cooling are somehow tied to the magnetic field's bizarre orientation, that single Webb observing program could end up answering 2 of Neptune's oldest unresolved questions at once. Stepping back, it helps to appreciate exactly how remarkable it is that any of this was even possible. Webb's instruments were built to detect impossibly faint light from galaxies that formed billions of years ago, near the very edge of the observable universe. Turning that same extraordinary sensitivity toward a planet in our own solar system, one that is comparatively enormous and much closer, so he required careful calibration because an instrument built to detect the faintest whispers of ancient starlight has to be handled very differently when pointed at a bright nearby planet. Yet Webb managed both. It photographed Neptune's rings with unprecedented clarity. It resolved 7 moons in a single frame. It captured the true color story that Voyager 2's imaging had. Distorted for decades, and then, almost as a byproduct of a routine atmospheric study, it detected an aurora that had evaded every previous search, and used that same signal to reveal one of the most surprising temperature shifts ever measured on a planet in our solar system. None of these individual discoveries happened in isolation. Each one builds on the last, layering onto a picture of Neptune that looks less like the static, frozen world of old textbook photographs and more like an active, changing planet with mechanisms scientists are only beginning to untangle. The rings that reappeared in 2022 reminded everyone how much detail had simply been invisible since 1989. The color correction reminded the public that even something as basic as what Neptune looks like had been subtly wrong for decades. And the aurora and temperature discovery reminded the entire scientific community that this planet's atmosphere is not the stable, unchanging system many assumed it to be. What makes this story especially compelling is that scientists still do not have a complete answer. They know Neptune's upper atmosphere has cooled dramatically. They know that cooling happened faster than the planet's own multi-decade seasons would predict. They know it lines up with an earlier independent finding of long-term stratospheric cooling. They know there is also a separate, seemingly unrelated cool patch elsewhere in Neptune's atmosphere. And they know all of this finally explains why the planet's aurora stayed hidden for over 3 decades. But what they do not know, at least not yet, is the underlying cause driving any of it. Is it tied to solar activity, ebbing and flowing over an 11-year cycle? Is it connected to Neptune's oddly tilted magnetic field? Is it some entirely internal atmospheric process that has nothing to do with the sun or the planet's magnetism at all? Right now, every one of those questions remains open. That open-endedness is precisely why this continues to be one of the most closely watched stories in planetary science today. Neptune, a planet most people rarely think about beyond a distant blue dot in diagrams of the solar system, has quietly become one of the most scientifically active targets for ongoing observation. Every new data point from Webb has the potential to either confirm a leading theory or completely overturn it. And because researchers are now committed to tracking Neptune across a full solar cycle, this is not a mystery that will resolve quickly. It is a slow, careful, multi-year investigation, unfolding in real time, with each new observation adding another piece to a puzzle that started with a single, unexpected reading buried inside data collected in June 2023. It helps to understand just how difficult it is to study a planet like Neptune from Earth in the first place. At roughly 2.7 billion miles away on average, Neptune is so distant that its light takes about 4 hours to reach us, and even our most powerful ground-based telescopes struggle to resolve fine detail on its surface. For decades, astronomers had to rely on indirect methods, watching for tiny brightness variations, tracking cloud features as they drifted across the disk, and building models based on fragments of information rather than a clear, continuous picture. This is part of why the 2022 stratospheric cooling study led by Michael Roman was so significant in its own right. His team had to stitch together nearly 20 years of ground-based infrared observations, painstakingly comparing measurements taken at different times with different instruments, just to establish that a long-term cooling trend was even real and not some artifact of imprecise equipment. That kind of research is slow, methodical, and easy to overlook, yet it laid essential groundwork. Without it, the Webb Aurora discovery in 2023 might have looked like an isolated anomaly rather than part of a broader ongoing pattern. This broader research effort has a name: Giant Climbs, a project backed by a European Research Council grant and led out of the University of Leicester. Its purpose is to study long-term atmospheric change across all 4 giant planets in our solar system, not just Neptune. The project has already uncovered similar long-term shifts in atmospheric temperatures and cloud patterns on Jupiter and Saturn, and it produced the very first detailed maps of stratospheric temperature on Uranus. Neptune's newly confirmed cooling trend fits into this larger pattern of research, suggesting that the giant planets of our solar system are far from static. They appear to undergo slow, complex climate changes of their own, shaped by forces scientists are still working to identify, whether that involves solar activity, internal heat flow, seasonal chemistry, or some combination. None of them have fully modeled yet. It is worth pausing on just how counterintuitive this all is. Earth's climate is influenced by variables we can measure constantly and in fine detail: ocean currents, greenhouse gases, solar radiation striking the surface, volcanic activity, and human industrial output. Neptune has none of these familiar drivers. It has no surface in the way Earth does, no oceans, no continents, no biosphere. Its atmosphere is composed primarily of hydrogen and helium, with traces of methane responsible for absorbing red light and giving the planet its blue-green hue. Deep beneath that atmosphere lies a mantle of water, ammonia, and methane ices, and at its center, a rocky core roughly the size of Earth. Given how fundamentally different Neptune's composition and structure are from our own planet, it might seem reasonable to expect its climate to be simpler, more predictable, governed purely by its distance from the sun and its long, slow orbit. Instead, scientists are finding a planet whose atmospheric temperature swings by hundreds of degrees over a matter of decades, in patterns that do not cleanly map onto its own seasonal cycle. If anything, Neptune's atmosphere appears to be more dynamic and less predictable than many models assumed, not less. This unpredictability is part of what makes the continued Webb observation program so important. The plan to track Neptune across a full 11-year solar cycle is not simply about gathering more data for its own sake. It represents a genuine test of competing explanations. If the cooling trend rises and falls in step with solar activity, that would point toward the sun's magnetic cycle as a driving influence, perhaps through changes in the amount of ultraviolet radiation or charged particles reaching Neptune's upper atmosphere. If, instead, the cooling continues steadily regardless of what the sun is doing, that would suggest the cause lies within Neptune itself, tied perhaps to internal dynamics, chemistry that changes over time, or interactions with its unusual magnetic field. Each possible outcome would send research in a completely different direction. And right now, nobody knows which explanation will turn out to be correct. The magnetic field angle deserves particular attention because it is one of the strangest features of Neptune that Voyager 2 first documented back in 1989 and that scientists still cannot fully explain. Instead of running roughly through the planet's center like Earth's magnetic field does, Neptune's field is tilted at a steep angle relative to its rotation axis and offset dramatically from the planet. This core. This produces a magnetosphere that wobbles and shifts as Neptune rotates, creating conditions unlike anything seen at Earth, Jupiter, or Saturn. Scientists have long suspected that this bizarre magnetic configuration might be connected to unusual internal dynamics, perhaps involving a thin, electrically conductive layer within Neptune's icy mantle, rather than a more traditional planetary dynamo. If the newly detected atmospheric cooling and the auroral activity are somehow linked to this same unusual internal structure, then continued study of Neptune's aurora could become an unexpected window into one of the most stubborn mysteries in solar system science, one that has remained unsolved for well over 3 decades. There is also a broader lesson here about how scientific discovery actually works, one that rarely gets highlighted in dramatic headlines. The team led by Mellon was not initially trying to solve the aurora mystery at all. They were studying atmospheric circulation, a comparatively routine scientific goal. The detection of H3+ emission, the confirmation of the aurora, and the resulting temperature. Measurement all emerged as a byproduct of that original investigation. This is an extremely common pattern in science. Some of the most significant findings arrive not because researchers set out looking for them, but because sufficiently sensitive instruments, pointed carefully at the right target, sometimes reveal far more than anyone expected to find. Webb's exceptional sensitivity, originally engineered for observing the faint light of the earliest galaxies, turned out to be exactly what was needed to finally catch a signal that had been too faint for every previous telescope to detect. For now, what we are left with is a genuinely strange scientific situation. A planet discovered in 1846, visited exactly once, briefly in 1989, assumed for over 3 decades to behave according to models built entirely on that single flyby, and then, almost by accident, revealed through a modern space telescope to be cooling in ways nobody predicted, hiding an aurora that only became detectable because its own atmosphere had quietly transformed while no one was watching closely enough to notice. Neptune, it turns out, has been changing this entire time, and we are only now catching up to what it has been doing in the dark, cold distance at the edge of our solar system. What makes this moment in planetary science particularly exciting is the timing. Webb is still relatively early in its operational life, and researchers already have a clear plan for follow-up observations stretching across the coming decade. Every future data point on Neptune will be compared directly against the 2023 baseline, giving scientists a rare opportunity to watch a distant world's atmosphere evolve in close to real time rather than reconstructing changes after the fact from scattered historical records. That kind of continuous, high-precision monitoring simply did not exist before Webb, and it changes the nature of the questions researchers can even ask. Instead of wondering what Neptune's atmosphere looked like decades ago, scientists can now track what it is doing this year, next year, and the year after that, building an actual timeline instead of a single frozen snapshot. There's also something worth noting about how this discovery reached the public. A single overlooked reading, buried inside a spectrum collected for an entirely different purpose, ended up producing headlines around the world. It is a reminder that some of the most significant breakthroughs in astronomy do not arrive through dramatic announcements or planned discovery missions. They surface quietly inside routine datasets, waiting for someone with the right expertise to notice that something does not match the models. Mellon's team was not chasing a legendary unsolved mystery when they pointed Webb at Neptune's middle atmosphere. They were doing careful, methodical science, and the mystery found them. So the next time Neptune comes up, it is worth remembering that this pale blue-green world at the edge of the solar system is not the static, sealed-off relic that Voyager 2's brief flyby once made it seem. It is an active planet, undergoing changes scientists are still racing to understand, watched now by the most powerful telescope ever built, with years of observation still ahead, before anyone can finally say exactly what is truly driving its cooldown.